Electromagnetic spectrum, Physical Sciences, Grade 10. Why is it that you cannot see in the dark? Why can you see more clearly when it is bright? What is the main difference between bright and dark? Light is the main difference, right? In the dark, there's less light, whereas when it is bright, there's sufficient visible light. Everyone is very familiar with light in everyday life. You can only see things because light bounces off them or is reflected off them and enters your eye. For example, light bounces off a tree, enters your eye, and you are able to see the tree. However, the physics of how you see is beyond the scope of this lesson. We are just interested in electromagnetic radiation. But why? Because visible light is a type of electromagnetic radiation, and in this lesson we will talk about all types of electromagnetic radiation, not just visible light. It is worthwhile to learn about visible light and other forms of electromagnetic radiation, as there are many applications using electromagnetic radiation. So, at the end of this lesson, I hope that you will be able to arrange different types of electromagnetic radiation in order of frequency or in order of wavelength. Give an example of the use of each type of electromagnetic radiation. Indicate the penetrating ability of different kinds of electromagnetic radiation and relate it to the energy of that radiation. Describe the dangers of gamma rays, X-rays, and the damaging effect of ultraviolet radiation on the skin. This is the electromagnetic spectrum, showing different types of electromagnetic radiation. There are 7 main types of electromagnetic radiation. We have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. We need to be able to arrange the different types of electromagnetic radiation in order of frequency or in order of wavelength or even in order of energy. Let's see how they can be arranged in terms of wavelength. The wavelength increases as we move from right to left. This means radio waves at the far left of the spectrum have the longest wavelength. Gamma rays at the far right of the spectrum have the shortest wavelength. As we move from gamma rays to radio waves, the wavelength increases. However, as we move from radio waves to gamma rays, the wavelength decreases. Let's now try to arrange them in terms of frequency, or let's see how they are arranged in terms of frequency. The frequency increases as we move from left to right. This means radio waves at the far left of the spectrum have the lowest frequency. Gamma rays at the far right of the spectrum have the highest frequency. As we move from gamma rays to radio waves, the frequency decreases. And as we move from radio waves to gamma rays, the frequency increases. There is a relationship between the frequency and the wavelength of a wave. The frequency of a wave, we say, is inversely proportional to the wavelength of that wave. As the frequency of a wave increases, the wavelength of the wave decreases. And as the frequency of a wave decreases, the wavelength of the wave increases. Let's look at gamma rays and radio waves to illustrate this relationship. Gamma rays have the highest frequency of all electromagnetic radiation. However, they have the shortest wavelength of all electromagnetic radiation. When the frequency is high, the wavelength is short. Radio waves, on the other hand, have the lowest frequency of all electromagnetic radiation. However, they have the longest wavelength of all electromagnetic radiation. The frequency of a wave is inversely proportional to the wavelength of a wave. Moreover, as we move from radio waves to gamma rays, the energy of the wave increases. This means radio waves have the lowest energy of all electromagnetic radiation. Note that the energy of a wave is directly proportional to the frequency. Radio waves have the lowest energy and gamma rays have the highest energy. The higher the energy, the higher the frequency. The lower the energy, the lower the frequency. That is why we say that the energy of an electromagnetic wave is directly proportional to the frequency of an electromagnetic wave. However, the energy of a wave is inversely proportional to the wavelength. The higher the energy, the shorter the wavelength. The lower the energy, the longer the wavelength. The energy of electromagnetic radiation is directly proportional to its frequency and is inversely proportional to its wavelength. This means the higher the energy, the higher the frequency, but the shorter the wavelength. The lower the energy, the lower the frequency, but the longer the wavelength. Next, we are going to talk about the different types of electromagnetic radiation separately, starting with gamma rays, which have the highest energy, and ending with radio waves, which have the lowest energy. Gamma rays are the most energetic type of electromagnetic radiation. Because of this high energy, they have what we call a high penetrating ability. For an example, they can penetrate skin and cause skin damage and cancer. Gamma rays also have valuable uses in our society. They are used for irradiation of foods and seeds for sterilization. They are used for sterilization because gamma rays kill bacteria by breaking down bacteria of the DNA of the bacteria. In medicine, they are occasionally used in radiotherapy or radiation cancer therapy. More commonly, gamma rays are used for diagnostic imaging in nuclear medicine, an example being PET scans. In astronomy, they are valuable for studying high-energy objects or regions. However, this can only be done with telescopes outside of the Earth's atmosphere. Last but not least, they can be used in medicine to sterilize medical equipment to remove harmful microorganisms. X-rays are also an energetic type of electromagnetic radiation. They have less energy than gamma rays, but still have more energy than the other 5 types of electromagnetic radiation. Because of their high energy, they can penetrate skin and bone. Overexposure to X-rays can cause cell damage and potentially cause cancer. X-rays have been used a lot in medicine, especially in something called diagnostic X-ray imaging. For people that want to study radiography after matric, you will be working with X-rays a lot. X-rays have many other uses, but the most common is X-ray imaging for diagnostic purposes. They can be used to diagnose cancer, fractures, and many other ailments. When someone says UV, the first thing that typically comes to mind is the sun or sunscreen. The sun is the biggest producer of UV radiation. UV radiation can be divided into three: UVA, UVB, and UVC. UVA rays have the longest wavelengths, followed by UVB and UV rays, which have the shortest wavelengths. While UVA and UVB rays are transmitted through the atmosphere, all UVC and some UVB rays are absorbed by the Earth's ozone layer. So most of the UV rays that you come across are UVA with a small amount of UVB. UVA are the least harmful of all UV radiation, and it is known that UVA does not cause sunburn. However, it can cause skin aging, possible skin cancer, as it can damage DNA. UVB are harmful and can cause skin damage, skin aging, and sunburn. UVB can cause skin cancer. As mentioned before, UVB rays are absorbed by the Earth's ozone layer, and only a small percentage are transmitted through the atmosphere. UVC are the most harmful of all UV radiation. However, lucky for us, UVC is not able to penetrate the Earth's atmosphere. The ozone layer absorbs UVC completely. Some uses of UV radiation include bacterial removal, and I've seen around some UV lamps. Visible light is the part of the electromagnetic spectrum that the human eye is most sensitive to. This is the only part of the spectrum that we can see. We cannot see gamma rays, X-rays, or UV, infrared, microwaves, and radio waves. Visible light is made of violet light, indigo light, blue light, yellow light, orange light, and red light in order of increasing wavelength. This means that red light has a higher frequency has a higher wavelength than violet light. However, earlier we saw that there's an inverse relationship between wavelength and frequency. The longer the wavelength, the shorter the frequency. This means that red light has a lower frequency than violet light. We cannot see infrared radiation, but we often feel it as heat. Near-infrared rays are used in electronic applications like TV remote sensors and photography. Their applications can be similar to visible light since their wavelength ranges are close. Microwaves can be used for communication purposes, as they can be emitted and received by antennas. Microwaves can penetrate material and deposit energy below the surface. This effect is used to heat food in microwave ovens. Microwaves are the main wavelengths used for satellite communication, wireless networking technologies such as Wi-Fi. Radio waves have the longest frequency of all electromagnetic radiation. This makes them suitable for long-range communication. Radio waves can also be emitted and received by antennas. Radio waves are widely used to transmit information across distances in radio broadcasting, television, two-way radios, walkie-talkies, and wireless networking. Radio waves are also used in navigation systems such as the Global Positioning System or GPS. Electromagnetic radiation is all around us. We interact with it every single moment of our lives. The benefits and uses of electromagnetic radiation are many. In this lesson, we do not even cover 1% of those uses or application. That is very exciting if you think about it, because it means you can go do your own research and discover a host of other uses and application of the different types of electromagnetic radiation. We've also learned about the dangers associated with high energy electromagnetic radiation such as gamma rays and X-rays, and the possible damaging effect UV radiation can have on skin. The most important takeaways from these lessons are that the frequency is directly proportional to the energy. This means the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Frequency is also inversely proportional to the wavelength. This means the higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. Energy is inversely proportional to wavelength. The higher the energy, the shorter the wavelength. The lower the energy, the longer the wavelength. Thank you so much for watching, and we've come to the end of this lesson.